Now, Griffith says that the divergence is a measure of how much V spreads out from the point in question. But please be careful, because that explanation is not sufficient to define what the divergence is, not even close. So to start this explanation, I want to go to figure 118a, which looks kind of like this. As a schematic drawing of a certain vector function. It looks like the vectors are diverging. It looks like V is spreading out. But just by looking at the directions of the vector V at different points cannot tell you whether the divergence is positive or negative or zero. The divergence of V depends on the magnitude of the function V as well as its direction. The divergence of V in this particular example shown in figure 1.18a is not just positive at the origin, at the center, but it's positive at all the other points as well. Griffith says that you can imagine V representing the flow of water, and you sprinkle some sawdust or pine needles on the surface of the water, and if the sawdust spreads out, then the divergence is positive, and if the sawdust gathers together, then the divergence is negative. Well, that's fine, except I get worried when I try to extend that picture into 3 dimensions. So let me tell you an alternative way of interpreting the divergence. Pretend that the function V is the velocity of a gas. I don't want to use water because I need something that is compressible for my explanation. Consider a particular point and imagine moving with the flowing gas. If the density increases, let's do it the other way around. If the density decreases as you move, then the divergence of V is positive. If the density increases as you move with the flowing gas, the divergence of V is negative. If the density doesn't vary as you move with the flowing gas, then the divergence of V is equal to 0. And the terminology is that the function v is incompressible or solenoidal. Those are names for functions that have divergence of v equals 0. I want to talk about the divergence in yet another way that's also mentioned by Griffiths. And let's consider figure 1.18c. It looks sort of like this. The vector v points upward everywhere, but as you move upward, the magnitude of v grows. If this were the velocity vectors of a flowing gas, you can see that in order for the gas to speed up, the distance between the gas molecules would have to increase and the density would be decreasing. And this is a situation with positive divergence. So the other way of thinking about divergence is in terms of sources and sinks, or faucets and drains. Positive divergence, if the divergence is positive at a certain point, and you wanted to talk about flowing water, there would need to be some magical faucet in space producing extra water that allowed the flow to go like that. So in figure 1.18c shown here, if this were a flow pattern of water which is incompressible, there would be no way for this flow to happen unless somehow additional water was popping out of nowhere all along the spaces to allow the velocity to increase without the space between the molecules increasing. In another diagram, you could have a negative divergence, and if that represents flowing water, there would need to be water disappearing down some magical drain in the middle of nowhere in space in order to produce that effect with incompressible flowing water.